In this section, we're going to talk about the inverse of a matrix and a couple of other topics. Before we discuss the definition of the inverse of a matrix, we need to talk about what is the multiplicative identity of a matrix. With matrices, it turns out that if you multiply a matrix times a matrix of this form, where you have down the diagonals from the top left to the bottom right, you have a square matrix, and then down this diagonal you have all ones and all the other entries are zeros, then we call these identity matrices. And the reason they're called identity matrices is that when you multiply any matrix by them, assuming the multiplication is defined, when you multiply any matrix by these matrices, it just returns the identity of the given matrix. So for example, let's say we wanted to multiply this matrix by the 2 by 2 identity matrix 1 0 0 1. Well, if you multiply this row by this column, you'll get 2 times 1 plus 5 times 0, which is 2. And then if you multiply this row by this column, you'll get 2 times 0 plus 5 times 1, which is 5. And then if you take the second row and multiply it by the first column, you get 3 times 1 plus 1 times 0, which is 3. And then when you multiply it by the second column, you get 3 times 0 plus 1 times 1, which is 1. And notice that this matrix is the same matrix we started with. And it also has to work the other direction. If we multiply this matrix, this identity matrix, from the left times any matrix on the right, as long as the multiplication is defined, it will return the same matrix. So let's try this. If I multiply this row by the first column, I get 1 times 2 plus 0 times 3, which is 2. And then multiply it by the second column, I get 1 times 5 plus 0 times 1, which is 5. And then let's take the second row and multiply it by each column. 0 times 2 plus 1 times 3 is 3. And then 0 times 5 plus 1 times 1 is 1. So you see here that if I multiply the matrix A by the identity, I get the matrix A. Or if I multiply the identity matrix times A, I get the matrix A. Now in the future, you don't actually have to do the multiplication, because it's kind of like knowing that if you multiplied with real numbers, 1 times 3 is 3. You don't actually have to multiply that, you just know the answer is 3. So if I were to see this in the future, I would know that this product is just 2, 5, the matrix 2, 5, 3, 1. And so I wouldn't actually have to multiply it out. The same thing on a 3 by 3 case, but if you're dealing with a 3 by 3 matrix, then you're going to be looking at a 3 by 3 identity. So this is the 3 by 3 identity, and I'll let you confirm that if I multiply this row by this column, I get 1. If I multiply this row by this column, I get 2. If I multiply this row by the third column, I get 3. And if I multiply the second row by the first column, I get 4. The second row by the second column gives me 5. Second row by the third column gives me 6. And the second row, the third row by the first column gives me 7. The third row times the second column gives me 8. And then the third row times the last column is going to give me 9. So you can see that when I multiply the identity here times this matrix A, the result is simply the matrix A. And then if I turn it around, and you can verify this one if you want, A, multiply it times I, and you're still going to get the matrix A back. So again, the identity matrix in matrix algebra is a little bit like the 1 with real number algebra or real number multiplication. But don't be confused. The matrix has to have, elements in it. So it's not like it's the number 1. It's actually a matrix that has this form with the ones down the diagonals and zeros everywhere else. Matrices also have an additive identity, but generally I don't worry about the additive identity because they're of little use. But a zero matrix, a matrix with all zeros, would be the additive identity. For example, if you took this matrix and added it times any matrix, it's just going to return that matrix. But we're not going to worry about the additive identity. Now, as I said, with real numbers, the multiplicative identity is 1. And the reason is because a times 1 is a, and 1 times a is a for any real number. But with matrices, that's not the same case, because matrices, you have to have a matrix and not a real number. Okay, now with real numbers, if you think about real numbers, for example, if you wanted the multiplicative inverse of the real number a, it would actually be 1 over a. And the reason these two numbers are inverses are because when you multiply them, you get 1, which is the identity. Well, the same thing holds true for matrices. If you have two square matrices and they multiply together to give a matrix identity, then they are said to be multiplicative inverses of one another, or we just usually just say inverses of one another. So, for example, with real numbers, the numbers 2/3 and 3/2 are inverses because 2/3 times 3/2 is 1, the real number identity. But with matrices, if you have two matrices like these two here that multiply together to give the identity, then these two matrices are considered to be inverses. So if you multiply these two together, you get an identity matrix, and therefore those two matrices here are said to be inverses of one another. So here's the formal definition of an inverse. If A is a square n by n matrix and B is another square n by n matrix, such that A times B equals the identity and B times A equals the identity, then B is said to be the inverse of A. Likewise, A is also said to be the inverse of B. And we give the notation like this to represent A inverse. Now don't get confused with this, because A inverse is not the same as 1 over A, because we don't have a reciprocal, so there's no division operation for matrices, so 1 over A would make sense anyway. Okay, to show that two matrices are inverses, it's pretty simple. First of all, they must both be square matrices, so the matrices can't have inverses if they're not square. And then if you want to prove that they're inverses, once you've identified that they're square matrices, just multiply them together. So here I have a 2 by 2 square matrix, and here I have a 2 by 2 square matrix. And not only do they have to be square, they have to be the same size to be inverses. So now let's multiply these together and see if we get the identity matrix. So if I take this row times the first column, I get 3 times 1 plus 1 times -2, so that's 3 minus 2 is 1. If I take this row times the second column, I get minus 3/2 plus 3/2, which is 0. And if I take this row times this column, I get 4 minus 4, which is 0. And then if I take this row by the second column, I get 4 times -1/2 is -2. And 2 times 3/2 is 3, and -2 plus 3 is 1. So you can see that their product is the identity. And generally it's good to show it in both ways, but it actually, if it works one way, it's going to work the other way, as long as the matrices are square, and they're square matrices and they're the same size. But I'll leave you to show that it also works the other direction. If you reverse the order of the multiplication, then you will also get the 2 by 2 identity matrix. Now, in order to find the inverse of a given matrix, there's some steps you can do, and I could show you this algebraically why it works, but I'm not going to do that here. I'm just going to go ahead and tell you what to do. So to find the inverse of an augmented matrix, to find the inverse of a matrix, if it's a square matrix, you can simply augment it with its identity that's the same size. And then you want to use row operations to transform the matrix from where you have the matrix on the left and the identity on the right to where you have the identity on the left, and then on the right you'll have another matrix. Well, that matrix on the right actually turns out to be the inverse of the original matrix. So it's kind of magically pops up, but there is some mathematical reasoning behind it and why it works. So let's give this a try. So if I want to find the inverse of this matrix, then what I'll do is I'll take this matrix and I'll augment it with the 2 by 2 identity matrix. Since that's a 2 by 2, I use the 2 by 2 identity matrix. Now, I want to get this side to be in reduced row echelon form. In other words, I want to make this a 1, this is 0, this is 1, this is 0. So we've done this in the past, so it shouldn't be too difficult to do it now. The first thing I'm going to do is multiply everything in row 1 by a third. So if I multiply everything in row 1 by a third, I'll get 1, 1/3, 1/3, and 0 for the first row. Okay, now you're going to use this 1 to eliminate the 4, and so I'm just going to multiply everything in row 1 by -4 and add it to row 2 and put the result in row 2. So -4 times 1 plus 4 is 0. -4 times 1, 1/3 is -4/3 plus 2. 2 is 6/3. So -4/3 plus 6/3 is 2/3. -4 times 1/3 is -4/3. Add it to 0, I'll get -4/3. And -4 times 0 plus 1 is just 1. Okay, so now I want this to be a 1. So I'm going to multiply by the reciprocal of 2/3, which is 3/2. And so if I multiply everything in row 2 by 3/2, that's going to give me 0, 1, -2, and 3/2. Okay, so now I've got the 1 here, and I want to multiply this 1 by -1/3 and add it to row 1 in order to cancel the 1/3. So -1/3 row 2 plus row 1, the result's going to go in row 1. So -1/3 plus 0 is 1. -1/3 plus 1/3 is 0, so I get 1 and 0. And then -1/3 times -2 is positive 2/3. 2/3 plus 1/3 is 1. And then -1/3 times a half, let's see, the 3's would cancel and I get -1/2. Add that to 0 and I get -1/2. So now you can see over here I have the identity matrix on the left, and so on the right I must have the inverse. Okay, so and now we want to go ahead and take this out because it's not complete until we identify the inverse. Make sure that our teacher knows that we know what the inverse is. So this would be the inverse of the matrix A, and you're welcome to check it by multiplying these two matrices together, because if they're inverses, their product should equal the 2 by 2 identity matrix. There's a practice problem down here that you can try on this. I do want to make one thing clear. For the 2 by 2 case, there's actually a formula that you can use to find the inverse of a 2 by 2 matrix, but I generally do not teach that, because what that does is that means that if you have to find the inverse of a 3 by 3 matrix or a 4 by 4 matrix, you won't have the tools to do it, because the formula only works for a 2 by 2 matrix. So I just go ahead and teach people how to find the inverse using the row operations that I did here. And so I'll do some more examples in the next video, and also I'll do some applications of matrix inverses.